Where I stopped last time was this embarrassment. Here we are, a course in nonlinear dynamics, and I'm going to spend a week, or as long as it takes, at least a week, until it sinks in, on matters linear. Now, the justification is, it's not so bad as it sounds. When they teach you general relativity, they teach you about curved spaces, but they teach you the way you learn about curved spaces is that you're in a local proper Minkowski frame. So, when you're evolving in that particular setting, as far as you're concerned, the world is flat, and as far as we are concerned, the world is flat. So it's not a bad approximation. It's actually a very good thing to start with, and then later you learn how to compute curvatures, etc., so you're not in a flat space. So it's totally legitimate. The main thing I want to do, I'll do something that is computationally, as far as I can tell, not very useful. There is an equation that says there are 9 components of Jacobian, and you integrate them along with a trajectory. There's nothing to it. But there is a conceptual thing that I think is very important to understand about dynamics. When we are given somebody's equations and we live in some arbitrary coordinate frame, this room, whereas what I'll describe today all happens in the co-moving frame of the representative particle of the state. In dynamics, there might be really a lot gained to understanding how to be in a co-moving frame rather than in some external fixed frame, because the external frames are very fixed and very stupid. They know nothing about what's really going on. So my origin could be there, but the goal is over there. The soccer game is happening very far away. And to understand what's really going on, you want to be in the co-moving frame. And stability is the simplest example of it. Solve equation in one dimension as a compound interest. So it used to be that interest was compounded annually or monthly, and the way it was done is that the derivative was replaced by your wealth at 2 different instants, divided by the interval of time, which could be 1 year or 1 picosecond, depending what you're doing. And that's proportional to constant per unit time, so it's a rate. And you rewrite this as x n plus 1, you multiply by delta, put on this side, and that's 1 plus delta lambda xn. And now, 100 years from now, you know what your pension plan will give you. If it's computed this way, it's going to be x100 will be, 101 will be this to delta t lambda 200 of what you started with. And Euler used this as one way to define an exponential. So he wrote this solution as a limit of many time increments. He replaced the total time by the number of increments. That's delta n. And in the limit of infinitesimal time, this is one of the definitions of the exponential. This is the simplest linear equation that we know how to solve. Exponential growth and exponential decay, depending on lambda is positive or negative. You could be also have taken out a loan and your wealth could be decreasing. And that works also for matrices. So if you take a matrix A, instead of just one rate of growth, matrix is your d by d rates. And if you go through the steps, this is one of the definitions of the exponentials. X d-dimensional vector multiplying x has a solution xt e to the t A of x at time 0. Basic definition of function of a matrix is that if you can write a Taylor series and you stick every place instead of, constant lambda, if you stick every place a matrix, that's one of the definitions of function of a matrix. So you'll have no hard time understanding what this exponential means. But I still prefer the way the actuary thinks. The way the actuary would write this solution would be to say that to d-dimensional vectors. So now we are in our setting x is now state space, which is d-dimensional, where d-dimensional can be anything from 1 to infinity depending on a problem. I can approximate this exponential by a product. I start with my initial state, x0, any place in the state space, and I apply to it this thing with lambda replaced by a matrix. So it's 1 plus time divided by number of steps, lots of terms like that, n of them, and the last term that could be written as the term by itself to the end, but you have to think about problem you're trying to solve. And our general problem is that we start at x0, and then we go some time, we end up at xt. And the way that this is done is that every place along we are using the local vector field to integrate our equation. So for example, it might be slow here, small vector, big vector. So this is v at x at time t. As we move around, our vector field in nonlinear problem is varying, it's not constant. And the matrix, stability matrix or matrix of velocity gradients was defined as the local shear, so it depends on the space. And we'll assume that we are in autonomous systems, so that law at given point of space is just given, it doesn't change in time. So the matrix of velocity gradients is by definition, how velocity moves me in direction I, this is the dimensional vector, if I make a variation in dimension xj, direction xj. So that means that A will vary with time as well. But now we have also definition for variable A. And now what happens is these are matrices, and in general matrices don't commute. So I'm not allowed to change their order. So this will now be my discretized product of n terms. The first time I will measure the shear around my initial point, and then we do it at the next step, delta t x1, where x1 is defined to be the value where the representative point is at time t1, and tn is the initial point plus n times. So these are little ticks on the trajectory. This is x1, x2, and they're just computational ticks, and this is xn. So then we have to evaluate the stability matrix at this point, and so on, until we end up at next to the last. And again, they have to be ordered because they're matrices. And what this means is that if you want to see things as they're happening, they're in a co-moving frame. We can write each one of these terms as e to the delta t. So to linear order, these things agree, plus order of delta t squared. So now if it makes you happy, and it apparently makes lots of people happy, you can now write an elegant formula. These are exponentials, so just multiply them. Then I see that I have sum over delta t's. When delta t is small, the sum is called an integral. So I can write this as e to the integral from 0 to t. So you can take a continuum limit. Now, this is totally illegal because they don't commute. So you can't just stick them into same exponential. If this is the same matrix, they'll be legal. But as they're different, when I multiply two matrices, two exponentials, there is something called Baker-Hauser formula, which hopefully you'll run into sooner or later, that says, yes, I can write it as a sum, but then I get a commutator term, etc. So honest thing would not be good. So instead of that, people say, aha, I put a letter here, and I call it time ordered. So if you were ever mystified by time ordering in quantum mechanics, it's the same thing. Whenever you have a linear problem and your matrix is changing in time, in quantum mechanics, the linear problem is the state space is called Hilbert state. The initial state is a point in Hilbert space, so it's a complex vector rather than real. This is called Hamiltonian, and this is an I over h bar in it, but it's the same thing as the way you solve linear problems. So whenever you have a linear problem on a trajectory like here, you have this situation. And in classical case, you can understand what it is. And I personally only understand it this way. I don't know what time ordering means other than moving and being sheared as I go along.